Okay, 8.6, we're solving logarithmic equations. Our goal is to solve logarithmic equations with one variable algebraically. Again, a very short lesson today. Relatively easy. We're talking about the Richter scale. So when we have an earthquake, we have a formula that we use to measure how strong that earthquake is. Okay, I'm sure you've heard of it before. The Richter scale. It's an exponential or logarithmic scale. So that means kind of as you increase from 5 on the Richter scale to 6 on the Richter scale, that's not as big as an increase as from, say, 6 to 7. Because it's a logarithmic scale or exponential scale, the higher you get on the scale, any sort of small increase is much, much greater. Okay, that's why, you know, if it's 8 on the Richter scale or 8.2, that's a much bigger difference than the difference between, say, 7 and 7.2. Okay, the Richter scale increases quite rapidly. So if you were to graph this, you could see kind of that relationship. We have R is equal to log A over T plus B, where A is the amplitude of the vertical ground motion in microns. So A is actually the number of microns that the ground moves up. T is the period of the seismic wave in seconds. So that's the length of time, or the amount of going through one cycle of that wave. And B is a factor that accounts for the weakening of the seismic waves. Okay, so that dictates how quickly they dissipate, or how quickly they weaken. One micron is equivalent to 10 to the exponent of -6 meters. So the question says, an earthquake measured 5.5 on the Richter scale, and the period of the seismic wave was 1.8 seconds. If B equals 3.2, what was the amplitude A of the vertical ground motion? So we're taking all of these values now and subbing them into the equation. All of these values here. We're subbing them into that equation. So we end up with this formula here. Okay, so until the introduction of all the logarithmic laws that we've learned, we wouldn't have been able to solve this. Okay, but now we should be able to. So we're going to rearrange the equation first by moving the 3.2 to the other side. And we end up with this equation. So you might be tempted to try and log both sides, but what you'll notice is we already have a log on one side of the equality. So that's not going to work. We don't want to log. So we can't actually log both sides. So we can't really do much here other than rearrange the logarithm into exponential form. So again, we're going back to the definition of what a logarithm is. Okay? This value, 2.3, is the exponent that the base needs to be raised to get this value. Okay, so another way to rewrite that is because we have a base of 10. 10 to the exponent of 2.3 is equal to A over 1.8. Any questions from there to there? That's by definition of what a logarithm is. Okay, that's what we've learned in the past.
So you wouldn't do like a log and exponent?
Sorry? No, you'd have log as I mentioned.
Oh.
Okay, you don't.
Simple question yesterday.
Sorry?
One of the questions was this yesterday. Like I had the same type of question.
No, it had the variable and the exponent. It was different. That you had to log and then use the power logarithm law to drop it down. Okay. Okay, so here we have now this equation, and we can use our simple opposite operations to solve for A. In this case. Any questions there? So now we just multiply 10 that's raised to the exponent of 2.3 by 1.8, and we get 359 microns for A. Any questions? Okay, pretty straightforward. Okay, example 2. Selecting algebraic strategies to solve a logarithmic equation. So again, we have an equation where we have a logarithm on one side but not on the other. We can't take logarithms of both sides. It's not going to help us. Okay, so we need to rewrite the logarithm in exponential form. So the base is x now, so we write it as x to the exponent of -2 is 0.04. Okay, then we could either solve this directly by, you know, putting 1 over x squared is equal to 0.04, and then x squared is equal to 1 over 0.04, and then take the square root, so x is equal to 1 over the square root of 0.04, plus or minus. Or what they did here is they found the same base and then related x to the base. Sorry, they found the same exponent and then x had to be equal to 5. Okay? Alright, B. Here in this case we have logarithms on both sides, both base 7. Okay, so just like when we have m is equal to n, we can do log m is equal to log n. We can go in reverse. Okay, so if we have, again, just one term on either side of the equality, not separated by addition or subtraction, not two terms, but just one term on either side, we can take those logs away. And so we're relating this term now to this term. So 3x minus 5 is equal to 16. Any questions there? Okay, and then we just simple operations and solve for x. X is 7. Moving the 5 to the other side, dividing by 3.
Oh, sir.
Yep.
I have a question on the earlier example.
Yep.
You know, one way you did it, you got a different answer than how the textbook got it.
Yeah, okay, so this is 1 over x, x squared, 1 divided by x. So this way, finding the base, would be the way that I would have used. Okay? And you can, if you find the same base, you're going to get the, if you find the same exponents, you can relate the bases and get the same answer.
Okay, then how about the one that you did? Well, why did you do it?
Okay, let's go back then. So what is the square root of 1 over 25? This is going to be 1 over 5. X squared this is no, this is the same answer. It's the same. Okay, if you take the square root of that, it should be 0.04 is 1 over 25, right? So this is x squared is equal to 1 over 25, which is equal to 25. So x is equal to 5. It's the same. Okay? If you were to just do that on the calculator, you'd also get 5. Okay? So either way is the same. Any questions? It just looks very different because it's in decimal form with a square root. But if you were to take 1 divided by the square root of 0.04, you'd get 5. Okay? So you could do it either way. Example 3. Here we have now 3 logarithms. We want to combine the 2 logarithms on the left-hand side. The reason we want to do that is because we want to eliminate our logarithms, and in order to do that, we can only have one term on either side of the equality. Okay? So we know by logarithm law, if we go minus logarithms, it's actually the quotient law. So we can put this value over this value. Okay, so going from here to here, you can also go the other way, from there to there. Any questions about that, from going from this step to here? Okay, once we do that, we have one term on either side, both with log 2. So the logs can cancel, and we're left with 6x is equal to 12. So x is 2. No questions there? All right, next one we use the sum law of logarithms. Here, the product law, sorry. So where it was an addition between 2 logarithms, we can combine those 2 values with the product. And again, now we have logarithm on one side, straight answer on the other. We want to go to exponential form, so we take the base of this, which is 10, raise it to this exponent, 12 is equal to x cubed. Now we take the third root, the cubic root, so if we have 10 to the exponent of 12 cubic root, remember this is 10 to the exponent of 1/3. So 12 times 1/3 is 4. Okay? So x is equal to 10 to the exponent of 4.
So can we 10 and the exponent like 12 over 3?
Yes. It's 4. Okay, and the reason we don't have to consider the negative side of this well, this is a cube root, but in this situation here where we had the square, we don't have to consider negative because remember these laws only work for positive values of m and n. Okay, so that you got to keep that in mind. Another problem, two logarithms. We want to combine those logarithms. They have the same base, so we can use the product law, combine them. Here we have binomial terms now. That's okay though, we just end up multiplying them. And we ended up getting a logarithm of a quadratic. Okay, because we multiply using the distributive property. And so we have log x squared minus 9 is equal to 4. So again, logarithm on one side, number on the other, you're going to change that into an exponential equation. I think they missed a step here. So from this step here, you would say 2 to the exponent of 4 is equal to x squared minus 9, right? The base 2 to this exponent is equal to this. Okay, that's where that comes from. Okay, and then we solve for x like we normally would. We get plus or minus 5. And you can actually check and you'll see if we use the negative value, left side does not equal right side. So that's what happens when we're using the negative value of x equal to 5. So we know x has to be positive 5. Okay, and we do that by checking, plugging them back in to the original equation.
So on the early step, where did the other logs go?
Where? From here? From here?
You know, in the beginning of the log.
Yeah.
Plus 3, yeah.
So these two get combined with the product rule, the product law for logarithms. So when you're adding two logarithms with the same base, that's the same as using one logarithm with those two values multiplied.
It wouldn't be like 2 logs something, the rest?
No, this is the product law of logarithms. So going from here to here.
Oh, okay.
Okay? Where you're separating by an addition, you can make that multiplication. Okay, so in summary, a logarithmic equation can be solved by expressing it in exponential form and solving the resulting exponential equation. So this happens when we have log on one side is equal to a number on the other. We express it in exponential form. So you take this base to the exponent of this as equal to that value. If log m is equal to log n, then m is equal to n. Important that the base, of course, is the same, a and a. Okay, so we can get rid of those logarithms if there's one on either side of the equality, one expression. Need to know a logarithmic equation can be solved by simplifying it using the laws of logarithms. When solving logarithmic equations, be sure to check for inadmissible solutions. A solution is inadmissible if the substitution in the original equation results in an undefined value. Remember that the argument and the base of the logarithm must both be positive. Okay, so that's important. Your base has to be positive and the value that you're logging has to be positive. But still, when you solve for a value of x, like we did here, I just want to restate this. X in this case could still be negative, where this whole value is positive. Does that make sense? Because there's a value here where x could be negative, and this whole value could be positive. there's a possibility, especially when we get into problems like this where we have x squared. So x is negative, say x is -1 here, this logarithm is still positive, right? So that, therefore, when you solve for x over here, you do have to consider both sides, positive 5 and negative 5x. Does that make sense? Because although we can't use those logarithm laws for negative numbers, when we have a number that's combined with another number, x in this case could still be negative, and those rules would still apply, right? Because it would still be a positive value here. If x was -2, for instance, you know, this would be -2, this would still be positive 4. Okay? All right. Any other questions?